So thus far we've been talking about net forces in horizontal and vertical, right? We've broken those down, horizontal and vertical. You guys know how to do that. We're now going to start focusing in on friction. Okay, we're going to look at different frictional forces depending on the surfaces that objects are acting. Okay, so in this last couple sections of chapter 4, we're going to look at friction in depth, and we're going to look at objects on an incline. So today our focus is friction. All right, and we're going to look at two different types of friction. The first of which is called kinetic. Kinetic friction. All right, we know friction in general acts in opposition to the object's velocity, right? It acts opposing the direction of the object's velocity. We know from drawing free body diagrams that friction goes opposite the direction of the applied force. Can you tell me what the word kinetic means? Anyone have any idea of the word kinetic or what it might mean? It means in motion, okay? It means motion. That's what kinetics means, motion. So we're going to look at the magnitude of kinetic friction, or the friction that something has when it's in motion. Okay, so when something is moving, do you think it has less friction or more friction than when it's sitting still? Less. Okay, when something is moving, it has less friction. You have to overcome less as you start moving. So kinetic friction has found to be proportional to the normal force. What's the normal force? Yeah, the force pushing up on you, or the table pushing back up on you, is the normal force. So this equation here, you're going to need to get used to, and I'll write it a little bit bigger here if it's too small. It says force of friction equals this little symbol here, which means the coefficient of kinetic friction times the normal force. Okay, so this symbol right here is called the coefficient of kinetic friction. Coefficient of kinetic friction. That's what this little symbol is. So we have to take that coefficient times the normal force in order to find our frictional force. So that means we need to become really good at calculating the normal force, right? So if an object is at rest, how do we calculate the normal force? What do we know the normal force is equal to if an object is at rest? Mass times gravity. It's equal to the gravitational force. Okay, that's going to be a big part of this. All right. The second type of friction that we're going to talk about here is called static friction. What's the word static mean? It's staying still. It's not moving. Okay, that's what static friction is. So it's going to be the frictional force that's applied when an object is at rest. Okay, you have to overcome static friction in order to get that object moving. You have to overcome that maximum amount of friction to get an object moving. That's static friction. The equation that we use for static friction, I'll write it bigger here. It says force max equals the coefficient of static friction times the normal force. Okay, and what force max here means is that it's the maximum amount of friction that keeps an object still. Or that keeps an object from accelerating. Just going to abbreviate accelerate, okay? So that's the maximum amount of friction that will keep an object from accelerating or from moving at all. Alex, can you put your phone away, please? Thank you. Okay. So this maximum amount of static friction keeps an object at rest, or keeps it from accelerating. All right, so this is the equation. The equations look the same. You're still solving for a frictional force. This maximum right here is still a frictional force. All right? I want you to turn to page 96 and read that last paragraph. Okay, if you didn't have everything I have written up, here it is again, but I want you to turn to page 96 and read this paragraph. It continues on to page 97. It's a little, it's like a, what's that called, a micro symbol. We've used it before. It's like a Greek letter. So it's like a U with like a little tail on the front.
It's mu.
Mu, okay. So it's a combination of an M and a U. Okay, so it's really a U, but it has a little tail on the front. So page 96. All right, so if we look at this last question, what do you think? Who thinks that kinetic friction should be higher? Who thinks that static friction should be higher? Yeah, good. It should be static friction. Anyone have an explanation as to why?
Oh, it's harder to move something from rest than like to keep it in motion.
Yeah, that's exactly right. It's harder to start something from rest than to just keep it in motion. Okay, very good. Page 97 has a chart with some values that I want you to look at. All right. This says a sled with a mass of 50 kilograms is pulled horizontally along a flat, snow-covered surface with a force of 75 newtons. Coefficient of friction is 0.010. So go ahead and get this problem copied down, and we're going to go through it. Okay, right now it's not asking for anything because we're going to walk through it step by step to get a final horizontal acceleration will be our overall goal here. But we're going to walk through them step by step so that you understand the process. Okay, so this problem, I've broken down the series of questions step by step so that we can see every step that has to go into these problems. All right, so our first goal is going to be to find the force due to gravity. Okay, before we do any of these problems, what's our very first step has to be what? Drawing. Yes, drawing our free body diagram. Good. Okay, so what all forces are acting on this? Gravity. What else? Normal. Yep, frictional. And the applied. Okay, so there's our free body diagram. We want to first find the force due to gravity. How do we find F sub g? Good, mass times gravity, very good. So F sub g equals 50 times 9.8, and we get what? $490. And we know that the units for gravity or force due to gravity are what? Newtons, good. And what direction is it going in? Down. Okay. So there's our force due to gravity. That's it. Everyone comfortable with that? Okay. As we move through the steps, my work is going to disappear on here, so just follow along in your notes and we'll move step by step. Okay? So next one, we want to find the normal force. If we go back to our free body diagram, what do we know about the gravitational force and the normal force? They're equal. So what do we have to do to even calculate the normal force? Nothing, right? We know that our normal force equals our gravitational force, and we already solved for that. So we know the normal force equals 490 newtons. Okay, and that's going to be going up, right? Are we there? Okay. Haven't lost anyone yet? Okay. Now we want to calculate the frictional force. We want to calculate F sub F here. Sorry. We want to calculate F sub F. What's our new equation for calculating the frictional force? Yeah, Cole. Cole.
The coefficient times the normal force.
Good. Coefficient friction times the normal force. Why did I choose to use the coefficient of kinetic friction? Number one, it tells us that. And number two, it's moving. Yes, both of those things. Okay? So we want to solve for force of friction. We know our kinetic coefficient is what? 0, 1. And what do we know our normal force is? Okay. So our frictional force then equals 4.9. What's my units? Okay, and what direction does our frictional force go in? To the left. Okay? So now we have our frictional force, we have our applied force, we have our gravitational force, and we have our weight force. Yes, Colin?
Do you want us to put the left arrow when we do the frictional force, or do you want us to put negative 4.9?
I would prefer you just to put the left arrow because we've built in the negative in our net force equation by taking right minus left. Okay? So now we want to find horizontal acceleration. How do we find the acceleration of anything? From what? We have to have our net equals mass times acceleration. Okay? But we need to get our big net force equation. So our net is going to equal our applied force. Oh, yikes. Applied force minus our frictional force, correct? Do I need to redraw the free body diagram, or does everybody have this equation? Give me like a head nod if you have this equation. Could you have done that step yourself? Okay, from our free body diagram, all we did was take the rightward forces minus the left forces. Okay, so those numbers are what?
75.
F net equals 75 minus our frictional force, which was 4.9. That means our net force equals what? 70.1. Okay, is this the acceleration? No. So I'm going to move this up here. Okay, 70.1 is our net force. We take net force equals to mass times acceleration. Our mass is 50 kilograms. We're going to solve for acceleration. So what's our acceleration equal to? 1.402. Okay, I don't need that many decimals. Meters per second squared. Okay, that's it. We did it. Okay, so these are the steps we go through if we want to find horizontal acceleration, which is most of the time what we're looking for. Finding our F sub g, then find our F sub n. Most of the time those two will be equal. Not every single time, but most of the time. Then we find our frictional force. Then we find net force. Then we can find acceleration. Okay, so those are the steps that we go through. If you would like to write those down, I think that would be a good idea, but it's up to you. Let's take a look at this problem. All it's telling us here is that we want to calculate acceleration of the crate. Do you think the acceleration they're talking about is horizontal or vertical? Horizontal. Good. Okay. Crate's being pulled horizontally. It's not even being pulled vertically. We want to find we want to find horizontal acceleration. So we know the coefficient, we know the mass, and we know the applied force. Let's go ahead and draw our free body diagram here. Is that what everybody's free body diagram looks like? Okay. we want to find F sub g. Okay, in this case, is F sub g going to equal our normal force? Yes. Why do we know that? Exactly. It's not moving up and down at all. So we can combine these two steps. That means the normal force equals mass times gravity, which equals 225 times 9.8. And tell me what that equals.
2,205.
All right. And that's newtons. And if it's the normal force, we know it's going up. Okay, what's our next step then? We found gravitational force, we found normal force. We want to find friction now. Okay, so F sub F equals our coefficient of kinetic friction times our normal force, which equals 0.20 times 2205. And that equals 441 newtons. And that's our frictional force, so it's going to be going to the left. All right. I'm going to get rid of this part here. We have our frictional force now. If we want to find acceleration, what's our next step? Good. Our net equals applied minus what? Friction. Good. So F net equals applied, which is 710, minus our friction, which is 441. And that makes our F net equal what? 269. Okay, so we can substitute F net in here for mass times acceleration. The mass we know is 225 times acceleration equals 269 newtons. And that means acceleration equals what? 1.2. What are my units? Okay, so let's go ahead and draw the diagram here. Here's my system. I have gravity. I have a normal force of some kind. I have friction. And then what's my applied force look like? Yeah, it's at an angle. Okay, my applied force is 100 newtons. But I need to break these down. Okay, so this will be our force applied X, and this will be our force applied Y. Okay, those are kind of small and hard to see, sorry. But you know what they're supposed to look like. Okay, so we have our diagram here. Our first step is always what? Force of gravity, okay? So F sub g equals mass times gravity, so 30 times 9.8. What'd you get? 294. That's F sub g. In this case, does F sub g equal F sub n? No, it does not. Okay, it does not because we're pulling on that box with some vertical force or some component of vertical force that's taking pressure off the normal force. So this is how we calculate normal force. Okay, our F net in the vertical direction will be our normal force plus our force applied Y minus F sub g. Okay, because if we take that triangle and break down those components and add them onto the correct axes here, this would be F sub g, we'd have F sub n, and then on top of that we'd have F applied Y. Does everyone see what I did there? We took our triangle components and added them to the correct axes. So this rightward force would be F applied X, and this would be the frictional force. Okay, so everyone see how I broke down those components and added them to the correct version of our free body diagram? Okay. So now to find the normal force, what do we do? How do you do it? We got to find this first.
64.3.
Okay, you guys can do that without me writing that down, right? 64.3. What's F sub G? 294. We found that. We want to find F sub n. Okay, what'd you get? 229.7. How do you know that? What's the net force in the vertical direction? What's the net force in the vertical direction? Is it moving at all vertically? No. Because it's just sliding. Okay, it hasn't come off the table at all. It's just sliding. So that means this net is 0. So we can move gravity over to the other side to have F sub G equal the normal force plus the applied force in the y direction. Okay, so what we just do there is take 294 minus 263, and we got 229. What did you say, Madeline? 229.7. Okay, did that step make sense to everybody? It's not moving at all in the y direction, so we know our net force is 0. We can move gravity to the other side, which we added over 294, and then we subtract 64.3. All right? So there's our normal force. Can I clear this screen okay? All right. We want to find the frictional force now if our coefficient of kinetic friction is 0.30. So we're solving for F sub F. We plug in our kinetic and we plug in our normal force, which we found to be 229.7. And what'd you get? Okay, that's our frictional force, and that's going in the leftward direction, I guess. Okay, so we just have a couple more steps. We want to find our net horizontal force here. So in order to find our net horizontal force, we need to find that applied force in the x direction. Okay. You found that from your triangle using cosine. 74.6, is that what you said?
76.
76.6, I'm sorry. Okay. We got that from breaking down the triangle into components, right? Do I need to do that on the board, or everyone got that part down? Okay, good. So we find our F net equals our applied, which is 76.6, minus our frictional force, which was 68.91. And we get what? That's our net force. Then we have 7.69 equals mass, which is 30, times acceleration to find our acceleration. Meters per second squared. All right.